Everything depended on a result no one would see. A spacecraft was about to disappear forever. It had no way home. No second attempt. No chance to report what happened after impact. If the mission succeeded, the evidence would have to come from somewhere else. The final images began arriving. A rough gray world grew larger with every transmission. Empty black space gave way to scattered boulders. Cliffs emerged from the shadows. Every picture was sharper than the last. Then the signal stopped. Exactly as the engineers expected. The spacecraft had slammed into the asteroid at more than 6 kilometers per second. That collision was never the proof. It only proved the spacecraft had reached its target. The real question survived the impact. Had anything in space actually changed? That answer would not come from the spacecraft. It would come days later, from telescopes on Earth, quietly watching the same asteroid over and over again, searching for a difference so small that missing it by a single minute could erase the entire mission. The asteroid itself had never threatened Earth. It was chosen for a different reason. A smaller moon circled a larger asteroid with remarkable regularity, completing the same orbit every 11 hours and 55 minutes. That predictable rhythm gave scientists something priceless. A baseline. If the orbit changed, even slightly, the universe itself would record the result. Long after the spacecraft had vanished, that orbit would decide whether the mission had succeeded at all. Humanity had already hit the asteroid. The investigation was about to discover whether the asteroid had hit back or whether its path through space had actually been rewritten. Night after night, the search had already begun. Long before anyone launched a spacecraft, automated telescopes were sweeping the sky with relentless routine. They did not wait for an emergency. They photographed the same regions again and again, comparing each new image against the last. Almost everything stayed exactly where it belonged. Then one tiny point of light refused to. It shifted ever so slightly against the unmoving stars. Not enough for the human eye to notice. Enough for software to stop and look closer. That faint movement was the first clue. Another asteroid had been found. The discovery did not come from dramatic explosions or giant telescopes staring at a single target. It came from repetition. Every clear night, wide-field survey systems captured enormous sections of the sky, searching for anything that moved while the stars remained fixed. One moving point became a set of precise coordinates. The coordinates became an official record. The record entered an international catalog that continues to grow with every new observation. The picture most people imagine is very different. It feels as though dangerous asteroids suddenly appear when someone spots them racing toward Earth. The evidence tells another story. Many of the objects capable of crossing Earth's orbit have already been discovered years, sometimes decades, before any close approach. Finding them is no longer a matter of luck. It has become a permanent global observing system. But discovery solved only the first problem. Knowing an asteroid exists says almost nothing about where it will be years from now. The first observations produce only a rough estimate of its future path. The possible locations spread across a wide corridor through space. Somewhere inside that corridor lies the real orbit. Everywhere else is mathematical uncertainty. One question still remained. Could that uncertainty ever become precise enough to tell us whether an asteroid would actually threaten Earth? For a newly discovered asteroid, certainty does not exist on the first night. Astronomers begin with only a handful of observations, a few positions, a short stretch of time. Enough to know something is moving, but not enough to know exactly where it will be years from now. The first orbital solution reflects that uncertainty. Instead of a single, precise path, scientists see a broad corridor of possible futures. Every additional observation narrows that corridor. Another night of telescope images removes possibilities. Another month removes even more. The future does not change. The measurements do. One asteroid became the clearest demonstration of this process. Apophis was discovered in 2004. Early calculations left open an extremely small possibility that it could strike Earth decades later. Those probabilities attracted worldwide attention, but they were never permanent predictions. They reflected the limited evidence available at the time. The investigation continued. Optical telescopes extended the observation record year after year. Then, in 2021, Planetary radar sent powerful radio signals toward the asteroid. The echoes returned with something ordinary to the eye, but extraordinary to the mathematics. Its distance, its speed, its position. With meter-scale precision, the effect was immediate. The uncertainty corridor that had once stretched across countless possible trajectories collapsed into a single, tightly constrained orbit. The remaining impact scenario for the year 2068 disappeared from the calculations. Nothing about the asteroid itself had changed. Only humanity's knowledge of where it would be. The investigation had overturned another assumption. Finding an asteroid does not immediately reveal its future. Prediction is built through evidence collected over time, each measurement replacing uncertainty with something narrower, until mathematics leaves almost no room for doubt. For the first time, the future of a potentially hazardous asteroid could be described not as a warning, but as a verified calculation. That raised an entirely different possibility. If an orbit could be measured this precisely, it could also reveal whether anyone had managed to change it. For centuries, prediction was the end of the story. If an asteroid's future path crossed Earth's orbit, humanity could calculate the danger. It could prepare. It could watch. But it could not intervene. Changing the motion of a celestial body belonged to science fiction far more than engineering. An asteroid weighing millions of kilograms seemed far beyond the influence of a spacecraft no larger than a vending machine. The mission challenged that assumption before it ever left Earth. Engineers were not looking for the largest asteroid they could find. They were looking for one that could answer a very specific question. Dimorphos was ideal because it did not travel through space alone. It orbited a larger companion called Didymos every 11 hours and 55 minutes. That steady rhythm could be measured repeatedly from Earth. If the orbit changed, telescopes would see it. The asteroid was not selected because it was dangerous. It was selected because it could reveal the outcome of the experiment with unusual clarity. By now, the familiar orbit had taken on a different role. It was no longer just another celestial motion to observe. It had become the measurement every engineer was waiting for. As the spacecraft closed the final distance, there would be no joystick guiding its last approach from Earth. Radio signals needed too long to cross the millions of kilometers between the mission and its controllers. The final decisions belonged to the spacecraft itself. Its onboard camera continuously searched the scene ahead. At first, Didymos and its tiny companion appeared as little more than bright points against black space. With every passing minute, the images sharpened. The navigation software separated the smaller moon from its larger partner and quietly adjusted the flight path again and again. No human hand made those final corrections. The spacecraft did. Then the asteroid filled the entire frame. Jagged boulders replaced distant points of light. Shadows stretched across an uneven surface. Every new image arrived only seconds before the next. The guidance never wavered. Then the transmission stopped. Exactly when mission planners expected it to. The collision had happened exactly as designed. But the investigation refused to end there. A successful impact proved only that momentum had been delivered. It said nothing about whether that momentum had been enough to change the orbit that had become the mission's true target. The spacecraft had completed its work. Now the evidence had to come from somewhere else. The most dramatic images from the mission were already public. They showed the spacecraft closing in on Dimorphos until the surface filled the entire frame. Dust, rock, and darkness followed. But those images could answer only one question. Did the spacecraft arrive? They could not answer the question that mattered. Did the asteroid's motion actually change? Within hours of the impact, telescopes around the world turned back toward the binary asteroid system. The collision was over. The measurement had just begun. Scientists were no longer looking for debris. They were looking for time. Because time was the only evidence that could not fake a new orbit. Before the impact, Dimorphos passed in front of and behind Didymos with remarkable regularity. From Earth, that motion caused the combined light of the two asteroids to brighten and dim in a predictable rhythm. For years, that pattern had repeated like the steady ticking of a clock. If the orbit had changed, the clock would drift. Nothing else needed to. Night after night, observatories recorded another cycle. Then another. One by one, the expected moments no longer arrived exactly where the old calculations said they should. The dips in brightness appeared earlier. Not once. Repeatedly. The familiar rhythm that had defined the system before the mission was no longer keeping the same time. One observatory might have made a mistake. Several independent observatories reaching the same result told a different story. The measurements converged. Different telescopes. Different teams. The same conclusion. Only then did the investigation return to the number that had been deliberately withheld since the spacecraft disappeared. Before the impact, Dimorphos completed one orbit around Didymos in approximately 11 hours and 55 minutes. After the impact, that orbit had shortened to about 11 hours and 22 minutes, a reduction of approximately 33 minutes. Far beyond the mission's minimum success requirement. The collision itself had never been the proof. The altered orbit was the recurring path around Didymos, once nothing more than a stable astronomical measurement, had become permanent physical evidence that humanity had intentionally changed the motion of a celestial body. For the first time, planetary defense had moved beyond prediction. It had entered verification. One successful experiment does not become a planetary defense system overnight. The measurements answered one question with unusual clarity. A carefully planned impact could alter the orbit of a small asteroid under controlled conditions. They did not answer every question that followed. Dimorphos is thought to be a loose collection of rocks held together by gravity, rather than a single solid block. Scientists are still refining exactly how much of the orbital change came from the spacecraft itself, and how much came from the cloud of material blasted away after impact, which acted like a natural recoil and added extra momentum. The engineering result was verified. Some of the physics is still being measured. Instead of treating the mission as a conclusion, space agencies treated it as the beginning of a much larger system. The next generation of planetary defense starts long before any spacecraft leaves Earth. Survey telescopes continue searching for objects that have not yet been catalogued, especially smaller asteroids that remain difficult to detect. Every newly discovered orbit becomes another piece of a growing map of Earth's neighborhood. Other missions now have a different assignment. Rather than striking an asteroid, they will return to the Didymos system to examine the aftermath in detail. By studying the crater, the debris field, and the internal structure of Dimorphos, researchers hope to understand why the impact changed the orbit by far more than the minimum mission requirement. The investigation has widened. It is no longer centered on a single spacecraft. It now connects discovery, prediction, intervention, and verification into one continuous chain. Break any link, and the system fails. Miss the asteroid, and there is nothing to predict. Predict the orbit poorly, and no mission can intercept it. Strike the wrong target, and there is nothing meaningful to measure. Measure the result incorrectly, and no future mission can know what actually worked. The first planetary shield is not a wall surrounding Earth. It is a process. Thousands of telescope images, years of orbital calculations, one precisely guided spacecraft, then months of independent observations confirming what the collision alone never could. Far beyond Earth, the binary asteroid system continues its journey around the Sun. Didymos follows the same solar orbit it always has. Dimorphos still circles its larger companion, but not on the same schedule. That quiet difference remains measurable from Earth. A single altered orbit now preserves the first verified evidence that humanity has intentionally changed the motion of a celestial body. The images ended at impact. The experiment didn't, because the only result that mattered arrived afterward.